Here's a really useful trick for computing determinants. The only drawback, it only works for the 3x3 case. I give you the diagonal trick for 3x3 determinants. Let's start with the checklist. First step, we're going to take our matrix A, put it right next to itself. It'll be important here to give yourself enough space so that you can clearly draw in the 6 diagonals. 3 to the left, 3 to the right. Then we're going to multiply down these diagonals. So if we multiply down the right, we're going to leave the signs alone. If we multiply down the left, we're going to change the signs. Then we'll take those 6 terms, add them together, and that gives your determinant. Now, for an example, let's consider the following matrix A. So I have row 1, 1, 2, 3, row 2, 0, 4, minus 1, row 3, 2, 0, minus 5. We put the matrix A next to itself. Note, I have enough room to clearly indicate the 6 diagonals. I multiply down to the right. Okay, so that'll give me a minus 20, a minus 4, and a 0. Okay, I leave the signs alone. If we multiply down to the left, I'll get a 0, and a 24. I'll change the sign on the 24, and then when I add, we get a minus 48. That you could check just using a regular row expansion or whatever definition you have for determinant. Here are a few things to be aware of if you're going to use this trick. First, the most common error is crossing diagonals because you didn't give yourself enough space. Okay? Like most of linear algebra, you need airtight bookkeeping. Okay, so here's an example where the second diagonal kind of shifts, and that's going to mess all the work up. So be careful with this. Next, okay, we might be wondering why this is true. So another common error is to think because we have this diagonal trick for 3x3 matrices, it's going to hold for 4x4 matrices and above. Okay, that's not going to happen at all. In the 3x3 case, it holds mostly by coincidence. So if I'm going to do a 3x3 determinant, I need 6 products. And it just turns out the 6 diagonals are going to correspond to those 6 products with the correct signs. If we go to 4x4 and above, okay, for instance, if I do the 4x4 case, you take a look at cofactor expansions, you know you need 24 products, but you only have 8 diagonals. Okay, we'll look at an example of that in a little bit. Now, just to show that it's true, okay, note if I just take arbitrary 3x3 matrix, okay, if I do a cofactor expansion along the top row, okay, that's going to look like this. I take my 2x2 determinants, then when I collect all the terms, okay, we note we're going to have our 3 diagonals to the right with a plus sign and 3 diagonals to the left with a minus sign. Okay, and so that you can take as a proof of that the trick corresponds to the regular cofactor expansion definition of determinant. Here's an example to show that the 4x4 diagonal trick doesn't work in general. Consider the matrix A. So I'll have rows 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, minus 1, and 1, 0, minus 1, 0. We apply the 8 diagonal trick. Okay, so we'll have 4 diagonals to the right, 4 to the left. Every diagonal has a 0 in it, so the products are 0, the sum is equal to 0. It's not difficult to see immediately that this matrix has determinant non-zero. Okay, for instance, if we consider the columns of A, okay, not difficult to see that they're linearly independent. Since we're in R4, 4 linearly independent vectors give me a basis, and the determinant has to be non-zero. Okay, to see that, just note if we manipulate columns 1 and 3 together, columns 2 and 4 together, we can get quickly to the standard basis. Now, to check this explicitly, okay, we'll see the determinant's equal to minus 4, so definitely not 0. What I'll do, okay, we take our matrix. I could first apply row operations. So I'm going to subtract off row 1 from row 4, and we'll take off row 2 from row 3. So we get to here, and then when I take the determinant of this matrix, we see quickly that we're going to get a minus 4, which is definitely not equal to 0. So you can't use the 4x4 diagonal trick in general.